Hello students, so in the previous class we started with higher order ordinary differential equations with constant coefficients, and we learned the method to solve when we have a homogeneous case, that means the right hand side is 0. If we have non-homogeneous case, then what shall we do? We'll learn in today's class. So let me just start with the equation directly. So I have introduced this operator already, right? So I have introduced this dn as some function of d, which is basically dn by dxn plus p1 dn minus 1 dxn minus 1 dot up to pn minus 1 dy dx plus pny, right? When you are doing this kind of differential equation, people usually use this FD. So of course I introduced this notation, but that's just for my reference. Let us call this as equation number 1. Of course it's not really an equation, but okay, we can call it an expression 1 just for the referral. Now we want to understand what is this symbolic operator FD, operator 1 by FD is actually 1 by FD, right? What is the symbolic operator 1 by FD? So if you go back to the differential equation, we have this non-homogeneous case that is of this type, right? This is our non-homogeneous case, which is basically FDY is equals to capital X. So it sort of tells us that if I mean how to say, bring this operator on the left hand side in this way, y is equals to 1 by fd of x, whatever this expression has a meaning, whatever this right hand side has a meaning, that is actually the solution y, because ultimate goal for this equation 2 is to determine y. We want to know the solution y. That means y can be a function of x, and if you substitute that y, then it must be equal to capital X, right? So that is the kind of y we are looking for. Now we are saying, okay, let us bring that fd by usual algebraic operation as 1 by fd, which is charged on x in a way, and whatever that will come out, that will be my y. So but what is this expression? I mean, we want to understand the physical meaning, or well, not physical in a way, but because then we are relating to applied maths problem. But what I meant to say is that we have to define this 1 by fd of x, right? So this is what gives us this particular integral, right? And the concept of particular integral will be motivated from this this expression here. So just to give you an idea, suppose we have something like this, d square minus of d. Keep in mind, d square means d square by dx square minus d dx of let us say we have x square minus of x. So as I said, it is d square by dx square minus of d dx of x square minus x. So if you do this derivative, then it will yield 3 minus 2x, right? So in a way, we are trying to say that x square minus of x is equals to 1 by d square minus of d of 3 minus 2x, right? This is what we mean to say. To give you more in terms of in simpler terms, suppose we have d of x is equals to d dx of x, which is equals to 1, and from here we can write x equals to 1 by d of 1. So if you remember, if you are doing d dx of a constant, let us say 1, then that is becoming 0, but here we are doing 1 by d. That means in a way it is an inverse of differentiation, right? It is an inverse of differentiation, and from traditional calculus, inverse of differentiation is kind of like integral. It is basically integral, right? So if d is the derivative, that means d dx is basically the derivative, then 1 by d which is not dx by d, 1 by d is basically the integral. So here what you are doing is you are doing integral of 1, and that is what is coming out to be x. So this 1 by d can be visualized as an integral, right, and that is why you are getting x here. So this 1 by fd is sort of like an integral, right. So here in this example you have 1 by d square minus d, that is sort of like an integral, but we don't know how to, for 1 by d it is very straightforward to write it as 1 dx, and then you get x. But for 1 by d square minus d, how to express this in terms of integral, that is a little bit tricky. So therefore we always try to break it off in terms of d only, so that you can put it as a form of an integral. Or if it is not possible, then there are several formulas, and those formulas are coming from some derivations, but you don't have to remember those derivations, you have to remember the formulas. That's a good news actually. And if you know those formulas, you can be able to write down the particular integral very easily, right. So the motivation is that this 1 by fd is kind of acting like an integral, and that is what we are looking for, 1 by fd of that function. And as you can see, it is always yielding a function of x. So that means dx equals to, if you had an equation dx equals to, let's say 1, then basically dy is equals to 1, then basically your y is equals to x is the solution, right. So this is what we are actually trying to establish here, and that sort of leads to the motivation of the definition of particular integral. Okay. So the operator, according to definition, the operator 1 by fd, according to definition, is the inverse of the operator fd, right, fd. And if fd is equals to d, then we have 1 by fd of x equals to 1 by d of x, which is nothing but capital X d of x. That's why I was saying that it's better to always get in terms of capital D, so that you can do this 1 by d of x, and that is basically your x dx. So this, and there are ways to find out this particular integral. So what will happen is, suppose for example, let us say that some way you know how to factorize this, right. I have found out that I can be able to factorize this. So this is d minus m1, then d minus m2 dot up to d minus mn of capital X, right. So then what will happen in this case, we will write this expression is defined by means that this expression is defined to mean that x is first inversely operated upon with d minus mn, and then the result is inversely operated by d minus n minus 1, m of n minus 1, and so on. until all the factors are simply utilized, are similarly utilized. So, after the first operation what will happen? So, after the first operation it becomes 1 by d minus m1, then 1 by d minus m2 dot and so on, e to the dot and so on, e to the power mn x capital X e to the power minus of mn x d of x, and we keep on doing this operation in succession, and it will give us e to the power m1 x e to the power m2 minus m1 x, then e to the power it will x e to the power minus of mn x d of x whole to the power n. That means this is dx 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 up to n times, and in all these integrals, so there are n integrals, everywhere this dx will simply get adjusted, right. So, therefore, let if we have a factor like this, our 1 by fd when charged over this capital X will yield an expression. So, this is equal to, not implies, this is equal to, will yield an integral of this type. Another way to handle this is, this is the first way. So, another way to handle this is that suppose 1 by fd, we all know this partial fraction, right. So, you have fraction of 1 by d minus m1, d minus m2 and so on. So, we can be able to write as some n1 by d minus m1 plus some n2 by d minus m2 and so on up to n by d minus mn, and then this is capital X. So, now this is again simple to handle, because then capital X will get distributed in all these places, and then from there basically we will have integral of, so from here we will have capital N1 e to the power m1 x x e to the power minus of m1 x dx plus capital N2. So, N1, N2 and all those things are constants, and we will have e to the power m2x capital X e minus m2x dx plus dot and so on, capital N e to the power mn x capital X e to the power minus of mn x d of x, right. So, by the way, here we are not bothered about constant of integration. So, because we are looking for particular integral, so it can also hold for c equals to 0. So, by default we are taking the constant of integration without loss of generality as 0, because it will not hamper the solution at all. Okay. So, this is one or the two ways to calculate the particular integral. Now, there are several formulas that I was talking about. So, the very first one is case formula 1, you can say, not that formula 1. So, formula 1 here, and particular integral for capital X equals to, let us say, e to the power a x, where a is a constant, suppose a real number, right, a being a constant. So, if your right hand side, now in this case we are saying specifically what is the given function. So, if the given function is e to the power a x, then what will happen? Then what will happen is, we have, so I will just show the derivation of one of them, and for rest of the functions I will write down the formula. So, we have 1 by fd of e of x. This is what we needed to find out, right. So, we have first of all d of E x. If I have d of E x, then it is a e to the power a x. If I have d square E x, then it will be a square e to the power a x. Similarly, if I take the nth derivative, then it is a n of e to the power Ax, right. So, therefore, Fd is basically Fd of e to the power Ax is what? Fd of e to the power Ax is we will have dn of e to the power Ax plus P1 dn minus 1 of e to the power Ax plus P2 dn minus 2 e to the power Ax plus dot dot and so on Pn minus 1 d of e to the power Ax plus Pn y, which is basically e to the power Ax, right. So, from here if I take e to the power Ax out, and this will basically become polynomial of A, correct, because all we will have is a to the power an plus P1 times a to the power n minus 1 and so on. So, right, it's a polynomial Fa. So, basically it tells us that from here it tells us that 1 by Fa e to the power Ax is equals to 1 by Fd of e to the power Ax. That means, if you are required to find out the particular integral of 1 by Fd, then in that case it will simply become 1 by Fd of e to the power Ax is equals to 1 by Fa e to the power Ax. This is in general, we just did the cross multiplication, but what we can actually do is that we can charge 1 by Fd on both sides. So, 1 by Fd is like an operator. So, if you charge 1 by Fd on both sides, then this will become e to the power Ax on the left hand side, and on the right hand side we will have 1 by Fd of Fa e to the power Ax. So, therefore, 1 by Fa will come on this side, and you will have 1 by Fd of e to the power Ax. So, this is what we have. If we are required to find out the particular integral of this e to the power Ax, then that will be the required answer, right. So, you can, provided of course here Fa should not be equal to 0. Provided Fa is not equals to 0, this is case 1, and if Fa is equals to 0, then in that case we have to take the d minus a factor out. So, since if Fa is equals to 0, then this implies that d minus a is a factor of Fd, and then this method fails. So, then what do we do? This method fails, and therefore, we write Fd equals to d minus a into phi d, right, into phi d, and this will become then we have 1 by Fd of capital X. So, this will become 1 by d minus a of phi d of capital X or e to the power Ax. So, here this is our e to the power Ax. So, d minus a phi d e to the power Ax. Now, for this one we can very easily write 1 by d minus a into e to the power Ax by phi a. So, this phi a will come outside, phi a, and we will have 1 by d minus a e to the power Ax. So, 1 by d minus a e to the power Ax. In this case, so of course, here we have to write provided phi a is not equals to 0, and from here 1 by d minus a phi a can be further written as 1 by d minus e to the power Ax can be written as x e to the power Ax by phi a, right. So, this is the required integral of or particular integral of given differential equation when Fa is becoming 0, right. Similarly, if d minus a square is the factor and so on. So, if d minus a square is a factor of Fd, then 1 by fd of capital e to the power ax will become x square e to the power ax by 2 psi a, where psi a is not equals to 0. Psi a is basically when you write fd is equals to x d minus a whole square into psi d. So, this is that psi, right. So, for exponential we find the particular integral in this fashion. There are other known functions. So, this is formula 2 when x is equals to x to the power m. So, then in that case 1 by f d of x to the power m is actually you have to expand this in terms of inverse binomial theorem, and whatever we will get, that means we write f d to the power minus 1 x to the power m, and then we do the inverse binomial expansion, and from there we charge xm in every term, and then we get the required solution. Third type is required formula. Third type is if capital X equals to sin ax or cos ax. So, this you will find, all this derivation you will find in the reference books that I have mentioned. So, you do not have to worry that even if I am not deriving here, they are very standard known results. So, you can find in any book. So, 1 by fd means fd of sin ax. So, we proceed same in the similar way the way did we for exponential, and this one will become 1 by fd. So, this will become only even powers. So, if fd contains only even powers of d, so then in that case we will have 1 by let us say. So, from here if it contains only even powers of d, then basically we will substitute let me write, if fd contains only even powers of d, and we denote it by phi d square, then we simply do phi d square, then we simply do 1 by fd is 1 by basically phi d square of sin ax, and we substitute d square equals to minus of a square, and that will be the required answer. Derivation you can look into any book. D square equals to minus of a square, and this is the required. So, provided this not equals to 0. Yeah. So, this is the required particular integral. Same goes with cos. If it has odd power, then what we will do, we will replace the d squares by minus of a square, and remaining d will remain as it is. Then we take it as an inverse, and we do this inverse expansion and charge the sign, right. Or we can multiply numerator and denominator by d and d plus a. If you have d minus a remaining in the denominator, then you multiply numerator and denominator by d plus a, and try to substitute d square equals to minus of a square in the denominator, and then you do the derivative in the numerator, and then you get the required solution. So, this is one way, and if it is becoming 0, so this is one way, and if phi a square is becoming 0, this then fd contains a factor d square plus a square. In such cases we do following. So, 1 by d square, we keep that factor separated, and then we do this cos of ax plus I sin of ax, right. So, this will be 1 by d square plus a square e to the power a I x, and this will lead to 1 by d plus a I d minus a I e to the power a I x, right. And then from here we know that we have to replace d by, so d plus ai is not equals to 0. So, this will become 1 by e to the power aix, right, aix ai plus ai, and the factor which is becoming undefined. So, that will become 1 by d plus ai minus of ai. So, we replace d by d plus a, and on the right hand side we will have 1 only. So, this will become 2aix by 2ai of 1 by d of 1. So, this is x a e to the power ix by 2ai. So, from here we can separate, it will become x sin ax by 2a minus of I x cos ax by 2a. So, from here we can compare and we will get the real and imaginary part, right. So, we will get and that is the required solution or required particular integral for cos ax and sin ax. So, just to give you a recapitulation, that when we have an nth order ordinary differential equation with constant coefficient. So, first of all we have to see whether it is a homogeneous type or non-homogeneous type. The minute it is homogeneous type, we know we have to just write down the auxiliary equation, and based on the roots of the auxiliary equation we can write down the solution y as a exponential or cos, a combination of cos and sin and all that. They actually come depending upon what kind of roots you have. So, if you have all the real roots and distinct, then in that case it will be just combinations of exponential functions. If you have some roots as equal but real, then you will have that polynomial type, then e to the power lambda x and another exponential functions. If you have complex roots, then complex roots occurs in conjugate pair, and therefore, there is a specific way to write down the solution. Now comes the question when we have the right hand side as non-zero. So, if we have the right hand side as non-zero, then we have to determine the particular integral, because the complementary function, it will come by taking the right hand side as 0. Now, for the particular integral, you write y is equals to 1 by f d of capital X. Now, if this capital X is exponential function, so then in that case we replace d by a, and that will be your required particular integral. So, it will be e to the power ax by f a, where f a is not equals to 0. Now, in case if f a is becoming 0, so then in that case we have to then in that case d minus a is a factor in there. So, what we will do, we will write d minus a times phi d, and then it will become 1 by phi d into d minus a into e to the power ax. So, you can replace d by a in phi, and the other part is 1 by d minus a into e to the power ax, and that can be handled by the technique that I have mentioned here, right, x e to the power ax. Then if you have d minus a whole square as a factor, then we will write as f t equals to d minus a whole square into psi d. Next, if you have x to the power m, so then in that case 1 by f d, you write f d to the power minus 1, and then you do the binomial expansion and you bring xm inside. So, if let us say you have up to when you are expanding when you are doing the binomial expansion, it will be 1 plus d square and so on, and here you only have x square. So, that means from third term and onwards it will simply become 0, because it cannot survive the derivative, higher order derivative. So, we know what will be the particular integral. Third type is that it can be sin x or cos x. So, if it is sin x, then the basic working principle is to replace d square by a minus of a square, and that will be your particular integral. Same goes with cos also. If your phi of a square is becoming 0, that means d square plus a square is a factor, and therefore we factor it out. We factor it out like phi 1 of d square into 1 by d square plus a square, because then phi 1 of d square, there you can substitute a square, and for remaining 1 by d square plus a square, you take help of this formula, and that will give us the required particular integral when d square equals to minus of a square. That means when d square plus a square is a factor, right. So, these are the few known functions for whom we know the particular integral, and in most of the cases when you are solving examples, if it is not a complicated problem, then in most of the cases you are given right hand side of a known function, so that you get familiar with the technique, the working principle behind it, and not to evaluate some complicated functions. So if you are given these known functions, you can directly use these formulas and try to solve them, and for the left hand side you proceed as usual by calculating the auxiliary function. So I will solve few examples on a constant coefficient in next class, and then we'll move on to the variable coefficient, but for higher order ordinary differential equation, where we will use this technique that we are learning in this class for variable coefficient as well. So I will stop here today, and we'll continue this discussion in the next class.